Now, I will say when I'm recording, don't walk in front of the camera, don't say anything. You got a question or comment, raise your hand, that's the thing. Reason being for privacy concerns, you make any sound on this, it can make you recognizable as a privacy violation if I post it. Okay, and we want to have these available. Okay, I can post it for you. I can post it within this group. I can post it on Canvas. You know how much I hate Canvas? Absolute. Gradebook is unusable. I'll show you what we'll do about a gradebook. I'll create one for you in my open math. Okay, then I can actually set the thing up. Your gradebook is unusable. You got to do two-factor authentication to get in and out. It's a pain in the behind. I don't use it. I use it for the introductory information that some of you all have already accessed. And incidentally, you got to do that. Okay, because you got an assignment almost right away. So you got to go to Canvas to get your access code for your master physics. Okay, the online text and everything. Also, your syllabus tells you you can also rent a physical text if you like having that. It's a little more expensive than the online. There's also physical text that's pretty good. I think it costs about $50 from OpenStax. If you're familiar with OpenStax. It's free online, and it's got some good features. Okay, I think a lot of the features are at least as good as some of the features in Mastering Physics. Okay, so it's a good supplement. You can use it online for free. You can edit the thing, make your own physics textbook. Okay, it's totally open source. Okay, anyhow, I want to get all that done. I've lost my train of thought. I probably should eat more for breakfast or something. I'll learn to regulate my blood sugar. Okay. Let's just start out talking about linear physics. Okay. Now, I said we don't want to talk because of privacy violations. I digressed into Canvas because what I was saying was that I can share this through Canvas. I really hate sharing things through Canvas. I can share it through YouTube. And there's already something that I can use to edit very easily. It doesn't have to go through all the Canvas rigmarole. Now, Canvas has some great features, but I don't think many of them are necessary for what we're doing here. So don't do anything that makes you recognizable with all the things we've done. Okay, now I'm going to turn the recording off so you can actually answer, and then we'll talk about it. No. Final position minus initial position. Okay. On a straight line. If it's along, say, the x-axis. Along the x-axis, it is positive or negative, or could be zero. Okay. If it's in the plane or in space, in an XY plane or in an XYZ space, then it becomes very clearly a vector quantity. Okay, and we'll suppress the whole vector quantity thing for right now. We'll just do it in one dimension. Okay. Okay. But these are rigorous definitions that you need to write a lot more words with qualifiers and stuff. So I'm just kind of saying, you're going to see it in your text. And that's more authoritative than I am. I never make mistakes, but still leave your text. Okay. I do make mistakes. Okay, average velocity. I also never can anticipate where the board's going to end. But it's the average rate of change in position. Okay. So we started out, got good answers, you know, when we talked about it a little bit. So how far do I go, how much time, and so forth. Okay. We want it to be a vector quantity. Change in position is a vector quantity. And along the x-axis, the vector is either a positive or negative. It only has one component. So you can just deal with it by plus or minus, but it's still a vector. Then, once you are used to the idea it's a vector, it's pretty easy to transition it into two-dimensional space, which is pretty easy to visualize. In three-dimensional space, which is a little tougher, and we won't do too much with it this semester. When you get multi-variable calculus, be able to make that transition. Okay, so we say that average velocity is the average rate of change of position. And we say the position is a vector. And on the x-axis, position is a vector, typically from the origin out to wherever you are. Could be vector in this direction, could be vector in this direction. Here's the key though. Average velocity, once you understand everything's a vector, is average rate of change of your position vector. Okay. What do I mean by average rate of change? We mean change in position over change in time, because that's the universal definition of an average rate of change. It's a change in this divided by change in that. Be sure that we understand it's change in time. It's the change in position. WRT stands for with respect to. Okay. You're going to see that abbreviation a lot, along with WTF, which stands for what's this foolishness. Okay. I don't know what y'all think it stands for. I've heard it in something else. What's this foolishness? Okay. Okay, so there we have it. Do you understand that? Make sense? Okay. Now, we just observed this rotating system and we took some data on paper. Fairly crude data, but still indicative. It's pretty obvious from the data we took that this thing is slowing down, right? And it will say that velocity is a vector. Just to confuse you, that vector is in this direction. You only can have one vector associated with that velocity. Any vector you put in the plane keeps changing, right? This thing goes around. So you're stuck with perpendicular directions. Use a right-hand rule and get your perpendicular direction. If you don't understand that, it's okay. Just giving you a little foreshadow. We'll define it when we have to. It's fairly simple. Okay, So change in position divided by change in time. We want to get some idea about how fast the velocity is approaching zero, because we know that thing's going to stop. Okay. So we have to define the rate of change of velocity. If you know how fast the velocity is changing, how quickly the velocity is changing, you can start making predictions, right? If you figure out from the data you took how quickly the velocity of that thing was changing during the 30 seconds you observed it, you can make a pretty decent projection if you assume the rate of change continues to be unchanging, how long it's going to take to stop. That makes sense? You know the rate at which the velocity is changing, and you have data that allows you to get a pretty good idea how fast it's moving, then you should be able to figure out when it's going to stop. Okay, again, if you assume that the rate at which velocity is changing doesn't change, changes at a constant rate, meaning that your velocity versus time graph would be a straight line. Okay, so let's put that together. Let's write something for that. Okay. Predict the stopping time throughout the rate at which velocity appears to be changing with respect to time. Okay. And assume that this rate, hope that this rate stays constant. Okay. So we hope that rate stays constant. Now we're doing an experiment. We got a hypothesis. If the hypothesis of constant rate of change of velocity holds, allows us to predict when it's going to stop, how long it's going to keep going. Okay. And then we can test that. If we can test it, if we can test it as opposed to contest it, if we are able to test that with sufficient accuracy, then we can come to a conclusion. Okay. Now I will tell you in advance that the rate isn't totally constant, but it's pretty close. So that we're either going to overestimate or underestimate our stopping time, assuming we have really great data. And we can actually test it using the computer interface. Okay. Or we can test it using our marks on the paper. And we can compare the predictive quality of the data this way and the data that way. Data that we actually take with our hands and understand, or data comes from a black box. Okay. But of course, when we've taken data with our hands, we know whether we can trust the data from the black box, and we can to an extent. Okay. Black box has its drawbacks. The system itself has a few little glitches. So it's very interesting to analyze it. Okay, well, where's this lead us? going to do a couple of definitions. We want to figure out the rate at which the velocity appears to be changing. You have enough data to sort of do that. You don't have enough data to do that very accurately at this point. But you can probably predict within 10 seconds or so with the data you have. I want to know what the names for some of these things are. We've got a name for the average rate of change of position with respect to clock time, right? So don't say anything yet, but what term would you use for the rate of change of velocity with respect to clock time? Okay. That rate is what we call acceleration. Okay. Well, we've got definition of average velocity. We've got a definition of average acceleration. And I should say average acceleration. Average acceleration. Okay, it's the average rate at which, no, actually I didn't say average rates. I don't have to put average there. Okay. If you know, don't answer just yet. If you know the position as a function of time, how would you find the velocity? If I give you a position function, how would you find a velocity function? Okay, well, pre-calculus, you learned this thing about difference quotient, and you used it in calculus to derive the derivative of x squared or sine x or cosine x, whatever, okay? You did that. If you had a decent calculus course, I know if you took it here, you do, okay? Limit of your differential to the difference quotient. Leads you to a derivative. Okay. Now, assume your position functions x of t, then your velocity functions d, dx of t, dt, right? And you can just write dx dt as long as you understand that's a function of t. Okay, we put that t in there when it's needed for clarification. Right now, since I'm just saying it for the first time here, okay. Break. Okay, this rate is acceleration, so acceleration is a function of t. So it's the derivative of the velocity function. And of course, that's second derivative of your, well, that was bad application of the equal sign, of your x of t function. Okay, this would be a 292 also. Okay, I'm writing it kind of small, but you know, this is the derivative of this. So the derivative of this is the second derivative of this, right? Should be pretty obvious. If not, go back and open your calculus or get one online or whatever. OpenStax calculus, which is great. Just go to OpenStax, OpenStax. Okay. And you see all kinds of things. Good to have one. It's good to have a physical calculus, but they're getting rare. Okay. Now, more briefly, P is dx dt. A is dv dt. Suppose A is constant. Say it this way, we can pretty much, I think I know how to write right now. Actually, we can pretty much solve, you see why I say pretty much in a minute. Solve dv dt equals A. Okay, anybody want to suggest how we might solve that? Okay, so we got dv dt equals A, that's a derivative with respect to t. So that with respect to, we had with respect to over here in our definitions of average velocity and average acceleration, right? At least average velocity, I think we can do with average acceleration. So we got dv dt equals A. There are various ways to find it, but I like the general antiderivative. You see from my integration constant, because you know now, if you take the derivative of AT with respect to, well, the derivative of T is just one, and leaves you A, and the derivative of a constant is zero, because it doesn't change. Remember, derivative is a rate of change. Okay, helps understand what these things are telling you. Okay. This means that for any, we can pick any C, and we get a valid velocity function. Now, sometimes your initial velocity is zero. So when t equals zero, velocity is zero, so c would be zero, right? If v is zero when t equals zero, that means your initial velocity is zero. Then you get zero here, and you get zero when you multiply this. Well, this one better be zero. Okay, think about it. It's pretty simple. Now you've done this in almost any calculus course right around October. Okay, you've seen differential equations like this. You didn't really, it's probably mentioned it's a differential equation. You don't have to use the techniques that many of you are starting to learn in your differential equations course to solve that equation, right? How many have taken differential equations right now? Okay, or have had it. And if you're not, that's okay. We don't use the heavy theory of differential equations in this course. It's not a prerequisite. But we still talk about some differential equations. Okay. A more formal solution of this. This isn't actually totally rigorous. dv dt equals A, so dv is A dt. You treat dt as an algebraic quantity, even though it isn't. And we got to prove that we can do that using limits and so forth, but we do it, it's safe. Okay, so we don't have to get deep into the theory of that. And then we integrate it from let's say T equals alpha, T equals beta. I want to go from A to B, but I'm already using A. So in a specific interval, dv doesn't depend on T. So we just get V of T and just simple integration. A is a constant, integrate dt, you get T. And then you substitute the beta and the alpha. So it can be written out kind of like this. I don't have time to say too much more about that, but you can write it out more formally. Okay. Okay, well, that's great. So we have a general function. We're going to use v sub 0 for the t equals 0 velocity. Okay, we'll call that the initial velocity. I could have written the AT first. It's okay. So we now know that for any motion, for the acceleration is constant. This holds. Okay. Then we can bring this up here. V equals dx dt, so dx dt equals v naught plus at. Okay. We integrate. Well, just formally, we can write this down. And then we can put an integral sign in front of these. And we get x, the integral of dx, equals one half at squared, at being what? The antiderivative of t being t over 2, t squared over 2. And I'll use x naught for the initial position. That's your integration constant. We're going to shorten time real short because we're out of time. Okay. Well, if acceleration is uniform, then we have a complete description of the motion. That's all we need. We need to know how to use it. It takes a little while to learn how to do that. You do that in chapter 2, I think. Maybe chapter 1. And it goes from there. Now, I'm going to email you a few questions about your data and stuff like that. I think it fits into this. I'm not going to master this. At least usually people don't master this for about a week. Okay. I'm not going to expect you to come in with complete mastery. I want to raise some really good questions come out of this motion. Okay. But right there's a nucleus. The analysis of motion, which I think is the first couple of weeks. Okay. Probably good to the understand this. It's a good start. Maybe, you know, I've heard some really good answers to things. Okay. And Jonathan kept quiet because he does a lot of mathematics. So I want him to overwhelm everybody. He'll have some good insights as we go. Okay, very good. I will see you Wednesday. You're going to need to log in, get everything together. If you're having a lot of trouble, do that. Email me. On Mondays, I'm usually around. a few hours after class. Today I'll be around for about an hour, but I got a doctor's appointment. Just a routine 6 month. Bill, 6 months.
So. You already turned your recording off this.
Oops. Yeah, we're violating your privacy, but you're okay.